like it all that much, and one day the axe just fell. Okay. The ideal gas law. What is the ideal gas law? So remember, standard temperature and pressure. So when we were talking about the thermodynamic stuff, delta H, delta G, change in entropy, all that stuff, standard conditions, there's always going to be a little bit of waffling over the temperatures. Some people use 20, some people use 25. Once upon a time, they used 0 degrees Celsius. It's annoying. For gases, there's no such confusion. Standard temperature and pressure for gases is 0 degrees Celsius and 1 atmosphere of pressure. Or it was. Now it's 0 degrees Celsius and 1 bar. Okay, so change is slow. We'll keep using atmospheres. The book uses atmospheres. Even though that's where I learned, I think that it's 1 bar. Anyway, the point is 0 degrees Celsius, 1 atmosphere of pressure is standard temperature and pressure. So now we're going to combine the gas laws. Pressure times volume is constant. Volume divided by temperature is a different constant. Volume divided by moles gives you yet another constant. Each of those letters, K, hides the things being held constant. In other words, within Boyle's law, the constant hides the moles and the temperature, such that this constant K will change depending on the different number of moles and different temperatures. Likewise, this guy hides pressure in moles, and this one hides pressure and temperature. So you can combine them to get a single law, such that PV over NT is equal to K, which is almost the ideal gas law. Little laws have their little constants, which are always changing because they're unique to each situation. The ideal law is universal. Therefore, we give it the universal gas constant, the capital letter R. Now, R's value is going to change depending on the units you're working in. So, first up, we rearrange it. We don't remember, long division is bad. So we rearrange it to get our ideal gas law. PV equals nRT. PV. And R changes its value depending on the units you're working with. So in joules per mole Kelvin, which is something you'll see in second semester if you keep on going with chemistry, it's 8.31451 joules per mole Kelvin. In liter atmospheres per mole Kelvin, it's 0.0820578. Or 0.08206, usually, liter atmospheres per mole Kelvin. Liter bars is 0.0831451 liter bars per mole Kelvin. And if you have it in pascals and cubic meters, it's 8.31451 pascal cubic meters per mole Kelvin, which you'll notice is the same thing as joules per mole Kelvin, because a pascal times a cubic meter is the same thing as a joule. And if you do it in liters and torr, then it's 62.364. And if you do it in calories, then it's 1.98722. Doesn't really matter. We are mostly going to be working with this guy up here, the liter atmosphere per mole Kelvin. And like I said, this one, joules per mole Kelvin, shows up some in the second semester. So let's do some PV math. What volume is occupied by 2.307 grams of hydrogen at 28.5 degrees Celsius and 775.65 torr? Well, first we need to convert to moles. So 2.307 grams of hydrogen times 2.01. Let's see. No, that can't be right. Well, let's just go ahead and bring up the calculator. Oopsie. And then, why did I multiply them? 1.0079 times 2. 158. Oh, I was right. Grams per mole. So 2.307 divided by 2.0158 is 1.144 moles. So now we have N. We also need to convert temperature from Celsius to Kelvin. So 28.50 degrees Celsius plus 273.15 Kelvin. Is 301.65 Kelvin. So now we have our temperature. And I'm going to go ahead and convert torr over to atmospheres. 775.65 torr times 1 atmosphere per 760 torr is 1.0206 atmospheres. So now we have our pressure. So PV equals nRT. So we're solving for volume. So V equals nRT over P is equal to 1.144 moles times 0.08206 liter atmospheres per mole Kelvin times 1.0206 atmosphere divided by, no, that was 301.65 Kelvin. So now we divide by 1.0206 atmospheres. So 1.144 times 0.08206 times 301.65 divided by 1.0206 is 27.746 liters. So yeah, 2.3 grams of hydrogen at a little above room temperature and a little bit higher, a little bit above 1 atmosphere pressure. So not an abnormally, not an impossibly high pressure. Occupies 27 liters of volume. Gases take up a lot of space. They just do. It's a huge amount of space. All right. So next problem. What pressure is exerted by 1.495 moles of oxygen at 475.28 Kelvin in a 35-liter container? Okay. This is going to be a pretty significant pressure, I think. So once again, PV equals nRT. This time we're solving for pressure. So P equals nRT over V. So 1.495 times 0.08206 times 475.28 Kelvin divided by 35.000 liters. So, calculator, 1.495 times 0.08206 times 475.28 divided by 35 liters is 1.666 atmospheres of pressure. What temperature is needed to get 25 grams of methane to exert 1 bar of pressure in a 5-liter container? Okay, so 25 grams of methane, we're going to need to convert to moles. (16.043 grams per mole). 1.553 moles. This is going to be a very low temperature, okay? Because it is 1 bar of pressure in a 5-liter container. Okay, so let's just go ahead with 1 bar and a 5 liters. So PV equals nRT. This time we're solving for temperature, so T equals PV over nR. So 1 bar times 5 liters, 1.5583 moles, and it's 0.0831451 liter bars per mole Kelvin. So 5 divided by 1.5583 divided by 0.0831451 means that in order to get it to exert only 1 bar of pressure, it's going to need to be 38.591 Kelvin. Very, very cold. It's like negative 340 degrees Celsius. All right, and finally, for this particular set of slides, how many moles of propane can you fit in a 10-liter tank with a burst rating of 65.32 atmospheres at room temperature? So, how many moles of propane? So this time we're solving from N is equal to PV over RT. The pressure, so it has a burst rating, so that's when it will burst. So that's the maximum pressure it can hold, so 65.32 atmospheres. And it is a 10-liter tank. And let's see, it's 0.08206 liter atmospheres per mole Kelvin. And the temperature is room temperature, so 298.15 Kelvin. So it's, need the calculator up, 65.32 times 10 divided by 0.08206 times 298.15. Boop and boop. 26.698 moles? That seems excessive. Let me think. 1 mole. So let's see. P equals nRT over V. So if we had 26.698 times 0.08206 times 298.15 in a 10-liter tank, would that really be 65 atmospheres? 26.698 times 0.08206 times 298.15. Yeah, divided by 10, so 65.32. Yeah, wow. Okay, so double checking my math. I did not make any mistakes when I put it in the calculator up here or anything like that. So yeah, 26.698 moles. Let's see. Oops. That's the molar mass of propane, so 44.096 times 26.698. That means that you can fit 1177-ish grams of propane in a 10-liter tank before it'll burst. I think that I might have actually gotten that from a website when I made this problem. That I actually Googled, maybe, perhaps, the actual burst rating of propane tanks. All right, so those are examples of Pfeffner problems. Not excessively difficult, I don't think. And that does it for the ideal gas law, which means that I am done for the evening. We will continue Chapter 9 next week.